when we compare the effectiveness of different optimization methods, it is useful to examine the rate of convergence of these optimization methods. The rate of convergence can be expressed in various ways, but a common classification is presented here. Before we talk about this rate of convergence, let's assume the optimization method generating the sequence of points xk is converging to x star. That is, when k approaches positive infinity, then xk is converging to x star. Now we can introduce these three rates of convergence. If this condition is satisfied, then the rate of convergence is linear. In this condition, we use the arrow at iteration k plus 1 divided by the arrow at iteration k. This ratio should be less than or equal to a constant c. C is greater than or equal to 0 and less than 1. From this condition, we can see the arrow at iteration k plus 1 is less than or equal to a constant c times the arrow at iteration k. That means the arrow at iteration k plus 1 is bounded by c times the arrow at iteration k. If c is equal to 0.1, then the error is reduced by a factor of 10 at each iteration. This constant c is called the convergence ratio. If this condition is satisfied, then the rate of convergence is order p. When p is equal to 2, then the rate of convergence is said to be quadratic. Let's suppose p is equal to 2, c is equal to 1. The error at iteration k is equal to 0.1. Then we can calculate the error at iteration k plus 1. Which is less than or equal to c times the error at iteration k square, which is equal to c times 10 minus 2. We continue to calculate the error at iteration k plus 2. Which is less than or equal to c times the error at iteration k plus 1. Well, which is less than or equal to c times c squared 10 minus 4. We continue to calculate the error at iteration k plus 3. Which is less than or equal to c times the error at iteration k plus 2. Well, which is less than or equal to c times c 4 times 10 minus 8. From this, you can see the error decreases very quickly. Before this condition is reached, only a few iterations are needed. If this condition is satisfied, then the rate of convergence is superlinear. The superlinear rate is usually fast in practice, as we have introduced the second method and Newton's method. Actually, Newton's method has quadratical convergence. The second method has a linear convergence. From the rate of convergence, you can also see Newton's method is much faster than the second method. In this topic, we introduced three different methods for one-dimensional unconstrained optimization problem. They are the bracketing method, Newton's method, and the second method. The bracketing method is a function value-based method. Newton's method and the second method are derivative-based methods. This is because Newton's method and the second method use derivatives. Usually, the derivative-based method performs much faster than the function value-based method. However, when the derivatives of a function cannot be obtained, then the function value-based method is better. We also discussed the advantages and disadvantages of these three methods in detail. Finally, we also defined three rates of convergence, including linear, order P, and superlinear convergence. As we mentioned, Newton's method has a quadratical convergence. The second method has a linear convergence. That means Newton's method performs much faster than the second method. I hope you can fully understand the contents of this topic. Thank you very much. See you next time.